Hey everyone, and welcome to the Postmortem for Team Sloppy Joe Pirates for MIT Battlecode 2026. So this is kind of a long talk, but I have three separate goals for this talk. The first goal is if you've never played MIT Battlecode and you're curious what it's all about, I hope I can convince you through the first couple of slides that it is a lot of fun and you should consider playing next year. It's a blast. The second goal is if you have played for a year or two, you know how the game works, but maybe you're not in the top 10 bracket quite yet. I want to show different strategies that I use to get to top 10 and top 4 in Sprint 2. And kind of show what I think is the meta currently and talk about different strategies you can use. And then lastly is a selfish goal. I hope that if you are watching this and you think I'm doing anything wrong, I would love feedback. I would always trying to get better. And if you think I'm not thinking about something correctly or approaching a problem correctly, I would love to hear your thoughts. That would be amazing. Cool. So for the rest of this talk, first I'm going to cover the game. This is kind of assuming you didn't play this year. If you played this year, please skip it. I'll talk about the game, what's involved, how to get started, what it kind of looks like. This is just to motivate people that haven't played and might want to play next year. Then I'm going to cover all the different high-level components. This kind of assumes that you have played before, but this is kind of how I split everything up and talk about the different strategies I used in these components. Then we're going to talk about my favorite thing, which is bytecode optimization. I'm going to talk about these different structures that you can use and you kind of have to design around for creating, winning strategies, I think. Next, I want to talk about Jinja templating and how amazing it is. And after reading Omnom's Postmortem last year, it kind of changed how I think about everything. And then some general thoughts on winning and what it takes. Cool. So this year's competition, it was Uneasy Alliances. And let me actually just load this up. Anyways, this is what MIT Battlecode looks like. Let me go to this one. I hope this competitor doesn't mind that I'm using them. I don't think they care too much. But we can see I'm hitting play. What we can see is we have a 2D grid. So this is MIT Battlecode. We're playing on a 2D grid, and your job is to program all these little units to go around and complete objectives and do certain things. Every year has a different challenge, a different set of objectives, but they all kind of follow a similar pattern. And that is that you're going to be spawning different units of different types to do things on the map. There's going to be resources. So this year's resource was cheese. There's going to be combat. You might see some combat happening up here. Rats. In this year, the units were rats. Rats can fight each other. In this year, there's usually bases. This year, the bases move around, and the bases are rat kings. These can spawn other units, and it's just a lot of chaos, but it's a lot of fun. You're programming these little things to do things on the board. There's a couple other things. There's things on the board. So we can see these are walls. So these are impassable objects. You can't move through them. We can also see that rats, this blue region, is their field of view. So they can't see anything except for things in this square. And so you can move certain places and you can look certain places, and that is all you can kind of like sense in your nearby surroundings. So you kind of have to remember where things are, and you kind of have to search and path around. This year they also introduced something new, these cats. This is kind of a unit that is not part of any team that just kind of goes around the board and creates mayhem. So anyways, yeah, this is the game. They provide a bunch of charts on the side. You can see like this is global cheese. You're collecting cheese. If you run out of cheese, you die. Cheese transferred kind of goes into the final score. Doing damage to cats also goes into the final score. And then you can also spawn new rat kings, and that'll also contribute to the final score. You can also see these are traps. This is one of the things that you can do for combat. Rats can bite each other. They can actually kidnap each other, called rat napping, depending on the position and the health, and they can lay traps. Once you kidnap a rat, you can also throw them, which you might see some of that over here. You can like chuck a rat at another rat, which does quite a bit of damage. You can chuck them at a wall. You can chuck them at a cat. You can chuck them at one of these big bases. And so like I said, the goal of this is you are going to be programming, you're going to be writing a program that every rat is going to run to decide its next move. The games last about 2,000 rounds, either 2,000 rounds and then it scores based off of some formula, or if one of the rats starves. For most rounds, I would say it's more common that a rat starves. Usually like a bunch of rats will like swarm the cheese mines and not let the other rats get access to the cheese mines. But yeah, it can either go to round 2,000 and it's scored, or one of the rats starves. Anyways, that's Battlecode. Like I said, it usually follows a similar pattern to this every year. And I think I covered everything. Oh, the last thing I didn't cover is to make sure that games don't last forever, you only get to execute so many instructions called bytecode. So if we actually select one of these rats, a little hard, you can see it's saying bytecodes used 8,000, 6,000. We're going to talk about that a little bit later, but it makes sure that every turn is fair. And it also shows that you can also see how there's move cooldowns, action cooldowns, and turning cooldowns. So you kind of have to balance that, like how many things you're allowed to do. Each rat is allowed to do is something you need to balance. And rats also can pick up cheese, and they have to deliver the cheese back to the rat king. So there's more to this game, but I hope that kind of gives a rough idea of what this game was all about. As to how you actually program these things, it's done in Java. So they release, the Battlecode devs release a scaffold. You can see it down here if you want, but it's just some Java code to help you get started. And this is kind of what the code looks like. So you could say, like, if robot controller can move forward, then move forward. And you can do system.outs to print stuff. If you want to turn, you can turn. There's a Java docs, which shows all the available methods. There's just a whole bunch of stuff. I'm not going to go through them, obviously, but can you place a rat trap? So one of those traps, can you throw a rat? How much dirt do you have? Can you move? All that sort of stuff. Can you sense nearby things? Again, it has to be within your vision cone. And so they release this API, and your job is just to use these tools available to create, the best structure you can. These go, once you have a rat or a robot that you think is good, you submit it to this online portal, play.battlecode.org, and it's very simple. There's just a command to generate a submission.zip. You upload it, and from there, it just automatically starts competing with the other submissions, and there's just a big leaderboard, and you can go crazy. So what's fun is you make a bunch of different changes to your robot, you submit it, and then you get to watch yourself kind of rise in the rankings. And it's just like a great feedback loop for learning and having fun. Cool. So that's the game. There was also supposed to be Python this year. I don't think it ever actually got finished, but maybe in future years there might be Python, but pretty much everyone plays Java. So the next section is components. So now I'm kind of assuming that you've played for a year or two, and this is just kind of like how I think about outlining things and all the major components, and I'm going to kind of talk about what these components do and any tricks or anything I've kind of discovered about them. The first component in my code was the component for baby. So this is baby.java. Technically it's baby.java.jinja 2, but we'll talk about that later. And I think the best way, every year we have some sort of like unit type soldier. And so for each one of these unit types, you're probably going to have its own Java class, which is going to like do things. And depending on how complex it is, it's either just going to do things greedily, which is what I did for the Rat King, which I'll talk about in a second, or most likely it's going to use some sort of like state machine. And whether or not you use a state machine or not, I think depends on if you have long horizon task. Like if you have a task that is going to operate over multiple turns, then I think it makes sense to have some sort of long-lived states. I found that for me anyways, the best way to do states too was obviously you can only be in one state at a time. And it used to be that I would store multiple variables per state, but I no longer do that. I think the logic, like your actual state machine is not just the states, it's also like the variables of that state. And your state machine, I think, explodes too fast and it's just too hard to debug and kind of frustrating to figure out what substate are you in. So instead now, when I do states, the only variable I store along with what state I'm in is the target location of that state. And it's useful for a couple of reasons. First off, we're going to talk about micro later, but I assume if you're continuing at this point, you already know what micro is, but it's the combat logic. One frustrating thing about microing is you don't always want a micro, and sometimes an important part of microing is like kind of skipping the micro and going towards what you're supposed to be going towards. Like if you have a bunch of cheese you're trying to drop off at the king, you don't necessarily want to fight people. You want to keep moving towards the king. And you want to kind of continue doing all of your objectives, not just that one. And so if you only have a single variable, which is like the target objective, it's very easy to plug that into your micro and say like, hey, like continue moving, towards the objective of the micro of your objective while you're microing and doing combat. And so like I said, I think it just makes things way simpler if there's just a single target for each state, and that's it. And you use the same variable. So you never get confused. You never have like leftover dangling state anywhere. I just found it made the code a lot simpler. Like I said, so how this actually works is at the beginning of each round, I will check to make sure that I am still in the current state or the current state is still correct. For example, if my state is picking up cheese, it's possible another robot could have picked up cheese, and that in that case, that objective is no longer valid, and then I should go back to the none objective. Or it's possible that I'm dropping off cheese, and I successfully dropped off my cheese, and I no longer have cheese in my inventory, so I should not still be in the drop off cheese state, in which case I erase that state and I go back to the none state. A bunch of these different objectives are I'm defending my rat king from enemy rats, and now the enemy rats are gone, so I no longer have to defend my king. So first step is to make sure I'm still in a valid state. If I'm not in a valid state, or If I'm not in a valid state, then I just go to the none state. From there, it's time to decide what my new state will be. And so I could either be in the none state or my previous state. And there are states that trump other states. For example, like if my king is under attack, that is probably more important than other objectives. Or sometimes I want to spawn a new rat king, in which case if I'm just like exploring around, like it is more important for me to spawn a new rat king, and that will kind of preempt the previous state. And so I decide what my new state will be, and then once I'm done with that, I will just execute the state. And once you know what state you're in, it's pretty easy to actually do the execute state. Like if you're down here, I have some sample code for pickup cheese. I'm just going to get the cheese target, which again, I only store one variable, and technically I store it in navigation, which I'll talk about later, but navigation get whatever the current target is, which is the cheese location. I decide if I'm going to micro, which I'll talk about a little bit later, but this is just the combat logic. I make sure I have a good path there, and then if I'm microing, I do the micro. If not, I just move closer to the cheese until I can pick it up, and then there's some logic down here that just says, if you can pick up cheese, pick up cheese. Very simple. Over here were all the states I used. This is a little bit weird, but none state is just do nothing or explore. It probably should have been 2 states, but I just keep it as 1. So if I don't have anything, I'm just going to go explore. And there's an explore module, which we'll talk about. There's the explore the mine. So I'm near a mine. We should go check it out. I think one thing I did differently than other teams is I left a unit on the mine at all time. I don't know if this is better. I did some A/B testing with leaving a unit on the mine and not leaving a unit on the mine, and it had very similar win probabilities. I do think that there is a defender's advantage in this meta. Because of just trapping and you don't want to be the person that initiates combat, I think leaving people on critical resources is good, but I'm not 100% sure. I think it is, but I think it has a slight edge, but I'm not 100% sure. So I always left someone on a mine. So as part of my states, one of the states would be, let's go explore this mine and see if there's another unit there that's sitting on the mine and being kind of like the guard for that mine. If not, then you can become the mine lookout, and then you're the rat that sits on that mine, and you just turn in circles looking for enemies, looking for cheese, and doing that. Another state is picking up cheese, so I saw some cheese, I'm going to go pick it up. As part of that pickup cheese, I also have to make sure that the cheese is easily accessible. Sometimes the devs make kind of weird maps where the cheese is like very far away, even though like it looks like it's close. So I just do like a simple thing. Can I move towards the cheese? And if I can, then I'll set my objective as pick up cheese. Otherwise I ignore it. And then there's also drop off cheese. I'm full of cheese, which we'll talk about in a second. What conditions you should go back and return the cheese. Report information. Either I have information about the symmetry of the map, which is very useful, or I have information about a new cheese mine, which a king should know. Part of this, I guess I didn't talk about it earlier. There's some communications in this game. For this challenge, or this year, there's a communications array that everyone can read from, and then the rat kings can write to, and then there was also squeaking, so rats can announce different things. But if I know symmetry or a cheese mine, I want to report that to the rat king, because exploring is kind of expensive, and I'd rather just know where those are, so then I can send rats to them directly. Then there's also defending king from rats and cats. Technically, this logic ended up getting squished into one. There's just one of these. I handle both of these at the same time. Yeah, if there's rats nearby, try to rat nap those rats. And if there's a cat nearby, try to squeak on the far side of a cat so it pulls the cat away. It doesn't actually work that well, but I don't know what else you're supposed to do with the cats. If you see an enemy king, you can go ahead and try to attack the enemy king. And sometimes we want to spawn a new rat king. To do that, you have to get 7 rats together. So the target is that new spot in the center where the new rat king will be spawned. And just like all the rats kind of swarm it until there's 7. And then we try to spawn. I think also very useful for debugging these and keeping this code as simple as possible is having an update state function, which is like, I want to transition from one state to a new state, and that new state will be new state, and also providing a string reason. This is useful for like why you're considering moving or why you are moving into a new state. Just helps with debugging a lot. So you can set that indicator string and also a log line. I just find it makes debugging a lot simpler. Instead of like willy-nilly like setting the current state somewhere, you must always use update state, and it's just like a very deterministic way. And then also the new location. I also store the previous state. This can be useful like if you're a mine lookout. Sometimes like instead of going back to none, if you're picking up cheese and you're a mine lookout, it makes sense to revert to your old state instead of going to a new state. But minor detail. So part of what I think makes a good Battlecode implementation, and I'm going to talk more about this later, is like answering a lot of just like these questions. And I think it's just like iterating on having good answers to these questions. And 2 of these questions for babies, and there's more, but 2 of them are, should I engage in micro? Micro takes a lot of bytecode, and you don't always want to engage in combat. And the other one is, should I drop off cheese? For the micro one, some of the questions that kind of go into this is like, should you micro a cat? And should you like engage in combat in a cat? And that's tricky. Like I think sometimes you want to. What I ended up doing was just like after a certain round, I think it's like 1200 or 1000 or something like that. I decided at that point that maybe we're going to go to all around 2000. And so I should start fighting a cat. But I think you could do it better. Like sometimes a cat might be blocking like a narrow pathway, in which case it does make sense to fight a cat. So knowing whether or not to fight a cat, tricky. I don't have a perfect answer to that. So I just did it based off of rounds. The other one is like baby rats. Are they accessible? So like here we can see all these rats are trying to fight these plum rats, but there's no way to actually reach them. So like these rats should not be in microcode, but they are. So making sure things are accessible. And the future is cat blocking the path. We already talked about that one. Another very tricky one is, should you drop off cheese? Or like in which case should you drop off keys? When you have 20 cheese, 40 cheese, 1,000 cheese, like when do you go back? And so the logic I used for this one was, do I also carry information? If I have information and some cheese, like I'm just going to go straight back. Like if I have information about the symmetry that isn't in the global array, then that is just head back. If I know a mine. If there's a bunch of enemies nearby and I'm outnumbered, it probably makes sense to go back. Again, this could be better, which I'll talk about later, but another reason. If nothing else, if I have 80 cheese, I just pick this number arbitrarily because it is faster than a cat. You have a movement penalty if you carry a lot of cheese. And I was like, you know what? Maybe I can always outrun a cat and that's good enough. I don't have a good answer for that. I did some math and I think it always makes sense to carry as much cheese as possible as long as you can safely make it back. But I think, yeah, making it safely back is the big question. Another question, like, a shortcut is, am I low in global cheese? And if that's the case, like any cheese I have, just like return it to the king. If the king is taking damage, like 20 is enough, just go back. And then the other one is like, am I asking this question because I'm at a mine and I'm just waiting for cheese and there's no nearby cheese? Or is there like cheese readily available and I should just like continue picking it up until like some hard limit? So I kind of hinted at like what I did for all of these, but these are the different conditions I was thinking about. And again, it's just a big function that, if one of these conditions is true, then I say, yes, I should drop off cheese, and I change states to the drop off cheese method, or that state. The next one component is king. This one was more of a greedy approach than a state machine because it doesn't really have long-term horizon objectives. Like at the beginning of the round, it decides, should I spawn a rat? And that's I should rename it. I called it desired rat count, but it should be like should spawn rat, which we'll talk about in a second. Should I move away from danger? So if there's a rat or a cat nearby, can I just move away from it? Should I pick up cheese? It used to be kind of a should, but now you should always pick up cheese because it counts towards the global cheese metric, which is not too important, but it was a rule change later. So can I pick up cheese? And if I can, you should do it. Is there any dirt in my way? Like I want to make sure that rats can successfully move around me. So if there's any dirt that's adjacent to me, I'll clean up that dirt. Pathing ended up being pretty important. Can I move to the center of mines as long as there's less than 6? And if there's more than 6, can I just sit on top of a mine? And the distinction for 6 is because that goes into my logic of spawning a new king. If I have 2, I don't want them both to go to the center of all the cheese mines. I want them to kind of sit on their own cheese mines and collect cheese from there. And then the last thing the king has to do is comms. And we'll talk more about that in the comms section, but they're just going to say where their positionings are. They're going to update the cheese mines so everyone knows where the cheese mines are, stuff like that. Kind of I don't know about meta, but the strategy for thinking about these things, how many rats should you have? And again, I'm going to talk about value frameworks later, but it's a tricky question. I feel like I don't know if there is a perfect answer, but the answer that I kind of was going off of is like, what is the map size? Like, does it make sense to have that many rats? Like, will the rats all have a purpose? Are there enough cheese mines to support like the continued production of rats? And then what is my global cheese? Like, do I have enough cheese? Even if there are enough cheese mines, can I support that many? Is it worth, spending 40 or 50 or 60 cheese per rat? And in the process, if I don't have that many rats, but I'm trying to spawn a new rat king, do I have enough rats to support the spawning? Like, because you need 7 to make a rat king, do I have enough to do that? So the function I used was just some kind of heuristics based off of that. I wish there was a better way, which I'll talk about in a second, but it's tricky. I don't know if there is an optimal solution. And then also should spawn new king. Again, very tricky. I don't know if there is an optimal solution to these questions, but it's just based off of round number. Like, if you're at 1950, you're about the end and you don't have a second rat king, you should just spawn a rat king pretty much no matter what, as long as you have cheese. If I already have a bunch of rat kings and there's not enough mines, then don't spawn any. Am I currently taking damage? In which case I think my rat king might die. Like, can I just hurry up and spawn a new rat king very close by? Is there enough mines to support multiple rat kings? I think we saw that each mine generates around like 2.5 or something like that cheese per round, and a rat king eats 2 cheese per round. So as long as you have mines, you can do it, but obviously then those rat kings can't spawn anything, they can't do traps or anything, so you need a couple of mines per king. And then do I have enough global cheese? The next question to answer is, where should you spawn a new king if you're going to spawn a new king? And what I ended up doing was going through all the cheese mines and scoring them. And so these are the scores I was using. Babies will report information about the mines they see. So does this mine have extra cheese that it was unable to pick up? Is it just a mine that hasn't seen anything? Is it a mine that has recently seen a cat? And is it a mine, I guess it doesn't have to be recently, has it just seen a cat at all? And is it a mine that has seen an enemy? And so based off of all of these, any mine, I'll take a grouping, so I'll look at a mine and I'll see all of the mines that are within 10 steps of it, like min of X and Y, 10 steps, because you can do diagonals, and then I'll add them all up. And as long as whatever mine is best and I should spawn a king, then I will mark that as the new king spawn location in the global array, and then a bunch of rats will spawn or swarm there and spawn a new king. But kind of stepping back to these questions, like philosophically, and I'm hoping maybe to get feedback from others if they have a good idea, but I'm trying to think of like, when you have these questions, I don't know if there is an optimal solution to these questions. And I'm thinking like, if there was an optimal solution, what would it look like? And I think it comes back to figuring out some sort of value function for how much value doing these things provides to your objective. And I don't know what these value points are. Like, do you relate these values to cheese? Is the value rat health? Some other currency? Is it the points? This is the point score. So if you get to around 2000, this is what the equation looks like. I guess I can go to slideshow. Whoops. This is the actual equation. I don't know. If anyone has an idea, I'd be very curious, but I do wonder if in the future, maybe we'll have some sort of like value calculator component to try to assess what the value of a certain action is. For example, like if I spawn a new baby unit, I should continue spawning baby units as long as I expect that this baby unit will provide more value than its cost. Again, I don't know what the value is and like how you would relate it to different things, but that is probably the most correct answer. Like, will this baby provide more value than its cost? And probably more value than any other things that I could invest in. Like for trapping, we haven't talked about too much yet, but a trap costs 20 cheese. Is it worth it? Like, is it going to help me complete my objective? I don't know. Like, it's tricky. I think somehow assigning a value to all the different things, like, is the enemy rat at 100 health, in which case then they're much more susceptible to rat trapping, or rat napping. Maybe it also depends on like how many rats are on the board. If there's only like, the enemy only has 4 rats, it probably doesn't make sense to trap them because the cost of them just making a new rat is cheaper than, the cost of 2 traps. At what point should you attack cats? Like, how much value do you get for a cat? Like, you get this score, but that value is constantly shifting. Like at the beginning of the game, it probably doesn't provide too much value to go and micro a cat, but near the end of the game, like, it provides a lot more value. And so I wonder, like, maybe the meta in the future will be like writing this like engine that can kind of shift between all these different currencies and calculating, what the value of something is, which is kind of fun. But anyways, I'd be curious if people have thoughts on that. Anyways, moving into some simpler components, because those are 2 of the more difficult or more the convoluted ones. Next up is explore. So the explore is also the none state, but if I have no pressing task, where should a rat go? And so some things to think about. The easiest one, or the spawn one, is the rat king will spawn rats, and if a rat has nothing to do, it will move from the direction of where the rat king spawned it and then go all the way to the edge of the map. And that just kind of go around and explore things. And so that's pretty much the only explore strategy I have. And then based on otherwise, if it doesn't have anything, it's going to think back to its memory, which we're going to talk about in a second. Have I seen any cheese that I just didn't pick up? If it remembers that there was some cheese somewhere, it will go back and pick up that cheese. It'll also think about cheese mines. So if there's no cheese, I will go back and I will iterate through all the cheese mines. Not all cheese mines are in order. It's going to go based off of the modulus of its own ID. So all the rats go in different randomness, or go into like a different iteration order. If it's seen all the cheese mines recently, it'll go look for the enemy king. Might as well go do some combat. And then if not, it'll just pick up a random square somewhere and go there. I didn't implement it, but I was thinking about doing some sort of like sectors, which other people have talked about. You can kind of divide the map into like little regions and make sure that every region has been explored, because missing a cheese mine is pretty detrimental to like surviving and winning around. Like you really need to know where all the cheese mines are. And so it's possible that like this rat could go all the way up and find a cheese mine, but then it gets killed by a cat. And because nothing else is going to go explore up there, we forever just lose out on that cheese mine unless we find it through symmetry. I think in the future I would do sectors, but I just didn't implement it this year. And it is also tricky. Like, what is the actual value? Like, maybe it'd be better to invest time in just making sure rats don't die. But different question. This year, there were 2 different ways to calm. So there was the squeak and there was the shared away. And so rats can squeak, and it's a radius of like 16 or something like that. And other little rats can hear nearby. And then the shared array was a global array that every rat can read from, but only the rat king can write to. So I don't think I did anything too complex with this. It definitely, there were lots of room for improvement. I just didn't need to. So for squeaks, what I ended up doing is just putting 2 messages into a squeak. And if the baby rat was microing, it would just say 2 enemy positions. I could definitely put a lot more in there. I got lazy and just never ended up doing it. But it would squeak 2 enemy positions that haven't recently been squeaked. And that is just to make sure for rat napping, you can rat nap if you're behind someone. So you just want to make sure that you don't let rats behind you. So I just always make sure that every rat nearby knows all the enemy positions. If you're nearby the king, you're going to be reporting information to the king. And so that could be the symmetry. So there's just a symmetry message, which gets encoded. It could be the mine if we found a new mine, which is always great, and store that into a global array. It could be the status of a mine. So does the mine have extra cheese that wasn't collected because I have too much cheese? That's great information to know. We should send more rats over there. Was I at a mine and I saw a cat? So maybe it's on a cat path. And so we just need to be a little bit careful, and maybe we don't want to spawn a rat king there. Or were there enemy rats there? So it's like a contested mine. And so maybe if you're low health, you should go to like a safer mine instead of going to the contested mine. Like I said, one thing I could do about this is I should be doing relative positionings. And so I could encode more information during micro. So I could probably encode a lot of enemy positions. I think, you only need 4 bits for relative positioning compared to 6. So I could probably, encode the position of like 5 or so nearby rats instead of just 2. For the shared array, this is the array that the king writes. What I ended up doing is just splitting up the slots. So 0 to 10 was just friendly kings. It was very inefficient, but it just didn't really matter. So each slot was 10 bits. And so I would just store the X and Y there. I think it's ended up being 12 bits, but so I had 8 wasted bits on every slot. Again, I wasn't really stressed for space, but I would store, each king would write every single round its current position into slot 0 to 10, and it would know what index it is based off of spawn order. Slots 20 to 58 would be the cheese mine and its status. So this would be like, this cheese mine has lots of cheese. There's a cheese mine at this location that has seen enemies, blah, blah, blah. Every once in a while, this would get updated. When it does get updated, the rats will read all of them. And they know if it's updated by reading slot 62 to 63, which is the last round it was updated. So this gets updated a lot in the earlier rounds, and then near the end, it's never updated. So there's no reason in reading all of these slots. If I want to spawn a new king, that'll get written, the position will be written into slots 58 to 60, and then slot 61 contains the current symmetry. Again, I should have, in the future, I would like to compress this a little bit. I mean, I'm not going to do this, but for this year, but to compress this more, and then also have as sectors. So like rats can see like which regions of the maps have been explored, and then if it's nearby a region that hasn't been explored, then maybe you can go explore that and then report it to the king that there's either something in the sector or there's nothing in the sector. Cool. The next component is opportunistic. A lot of code lives in this initially, and then eventually it kind of dwindles down as I have more intelligent strategies. But these are just like greedy things that you can do at the end of your turn. And so like at the start of Battlecode, I would have things like rat nap. Like, am I able to rat nap? And if I can, then I should just do it. And so I'll rat nap an enemy. This is an example, a bite. Like maybe I'm at the end of the turn, I have extra actions. I can just check because it's so cheap. Can I attack the position forward of me, to the forward left, or to the forward right? If I can, and I have action, like might as well just do it. So I'll do an opportunistic bite, and I'll spend my actions points that way. And there's a bunch of things I do. Like, maybe I won't go out of the way to pick up cheese, but it's possible, like while microing, I just end up next to some cheese, so might as well pick it up if I'm not doing anything else. If there's some dirt in my path while microing, maybe I'll just clean it up real quick. Maybe through microing or just doing something else, I happen to be next to a king, and I I have like 20 cheese, not enough that would facilitate me to like explicitly go back and give it to the king. But if I'm already next to the king, might as well drop it off. If I have any information I wasn't going to report, but I just happen to be next to a king, I'll report it. Can I bite? And maybe I haven't turned and I'm not like microwing or doing anything specific. Maybe I can turn in, some random direction to get some new information that I previously wouldn't have gotten. So I find what happens for the opportunistic, it probably could live in like either baby or king, but they both use a lot of it. And like I said, I'll have more code in there, but then as I like refine my strategy, I move functions out of opportunistic and like actually have a real implementation. Next is the symmetry class. I don't think symmetry was as important this year compared to previous years, because I think previous years you really want to know where the enemy base is. And this year I don't think it was quite as important because enemy bases move and there might be multiple enemy bases, but it was very important for cheese mines. And so if you have the map is either horizontally, vertically, or rotationally symmetric. And so just knowing where one of those, which one it is, like you can potentially double the number of cheese mines you know about. I think the trick too to symmetry isn't figuring out what the symmetry is, it's figuring out what symmetries it isn't until you're only left with one. And so like you'll have some sort of like check symmetry function, and what it will do is it'll just say like at this location I saw a cheese mine. Does that invalidate? Have I seen the symmetric position for either rotational, horizontal, or vertical? And if I have, was there a cheese mine there? And if there wasn't a cheese mine, then we know it's not that symmetry, and so we can remove it. And obviously you only do that for permanent structures. So in this case, this was walls and mines, because you can move dirt and you can move rat kings and stuff like that. So the next component is memory. So what should you remember about the map? And also like what should you remember about the map for that current round? So we're going to talk about fast arrays in the bytecode hacking section, but basically just think of them as like an array list. And so what we're going to do for the memory section is we're going to iterate through sense nearby robots and sense nearby map infos and kind of pluck out the information that we think is interesting and save it for later. It's not, and the reason we're doing this is not that sense nearby robots or sense nearby map infos is expensive. What's expensive is iterating over these structures. So each iteration costs like 10, and there's a bunch of if conditions you're doing in there. So it ends up being like, 2,000 or 3,000 to iterate through everything here. And so you only want to do that once, 2,000 or 3,000 bytecode. And I save a whole bunch of stuff, a whole bunch of things that I pluck out that I think might be interesting for later. And so some of them might be walls. I should know where all the walls are, if that region is passable. Have I seen this area before? Is there a cheese mine there? Dirt or cheese? These are kind of, I call them flaky sets because they can change. And then I save a bunch of round specific stuff like, did I see this location this round? Did I see a mine there? Cheese, a friendly baby, a friendly king, enemy baby, enemy king. Did I see a cat there? Am I able to place a trap there because there is no trap there? Am I able to place a trap there? And you can't also place a trap on a cheese mine. Is it adjacent to a trap? In which case later I don't want to place a trap there, which we'll talk about later. Is it round and passable? Due to dirt, wall, enemy robot, or a fat robot, or a cat robot. Can I attack there? Friendly. A bunch of combat stuff like, is it nearby a cat? Did I see an enemy baby here? Did I hear a nearby enemy through squeaks? And is there a cheese mine that I saw that isn't known by the global array that eventually I want to report? So a bunch of stuff. And then I also store, did I see a cat at a cheese mine? Did I see an enemy at a cheese mine? Did I see extra cheese at a cheese mine? And was this cheese mine from a squeak? So that's memory. Like I said, it costs about 3,000 to go through and calculate all this stuff, but we just do it once. Iterate through both of those big arrays, the nearby robots and map info, and then store anything we might want for later, and then we're done with it. And again, I'll talk about fast arrays later, but they're just like nice little containers that you can do a bunch of stuff with. Cool. The next component is pathing. So the pathing algorithm I ended up using was predictive bug with relaxation. Elsewhere on this channel, I have a video where I was kind of exploring different pathing algorithms, and I think I said this is the one I was going to go with. And I think I'm pretty happy with that choice. I think if I was to step it up, I would probably have two pathing algorithms. I would have a simple bug, and then I would use one of the bytecode optimized flood fill or something. But if you're only going to have one pathing algorithm, I think predictive bug with relaxation is very good. And so what is predictive bug with relaxation? I'm assuming you already know what bug is if you made it this far in the video, but bug nav is just wall follow. But with predictive bug, you are able to step forward through many iterations, and this is using your memory. So if you know where all the walls and units or locations that you've seen already, you can use that to kind of predict pretty far into the future and create long paths of where you're going to go. And then when you have spare bytecode at the end, what you're going to do is you're going to relax the path and basically just going to optimize the path quite a bit. So we can imagine we had a structure like this. So the black one is the wall, the green is the wall following path that was generated. Obviously, it's pretty silly to go down these. I think this was in a map called like parking structures or parking spots or something like that from last year. But you can imagine if you're wall fall or doing bug nav, you're going to go into this, and that's just a complete waste of time. So what we can do is relax, and relax is not super efficient, but again, it's just something you do with spare bytecodes, is you go through the path and you ask 2 questions. The first question is there any way I can go from 1, so this, let's say this is 1, 2, 3, can I go from 1 to 3 directly and just skip 2? If you can, let's just remove 2 from the path. Like, we don't need it. So we can remove this one and this one. They're just not needed things. The next time we go through, technically it's the same iteration, but depending on how you write the algorithm, we're going to go through and we're going to ask from 1, 2, 3, is it faster? Can I get to from 1 to 3 in a faster way? And by faster, I mean, is it closer? So I could go from here to here to here, and this one is closer to the final goal, because this is square root 2 and this is just 1. Again, this doesn't actually make a difference. It just sets it up so that we can make a difference later. So this square is closer to the final goal than this square. When we do it, we have something that looks like this. So we moved for this one to here and this one to here because they're just a little bit closer, even though it's the same number of steps. It's just a little bit closer on the path. And then from there, we can ask that adjacency question. It's actually, so sorry, we do is 1 closer. So this to here is not closer because we have to go diagonal. But from going from 1, 2, 3, it's closer if this was in the middle. So let's just go in the middle, even though, again, it's the same number of steps, and then go back. But then this allows us to then do the adjacency thing and continue like kind of carving it away until eventually we would get to just all the way across. Like, we don't need to go down this crevasse. And this was kind of an interesting example, but a lot of them are usually just like you're heading towards a wall and you just kind of, like when you bug nav, you hit a target and then you follow that wall. Most of the time you just kind of like carve away that turn so you can make the turn faster instead of like hitting the wall and then going, which definitely saves a lot. And it's nice. You can save, using that relaxation, you can save quite a bit of steps and get a pretty optimal path as long as you have a path that gets you to your target. The other cool thing that you can do with this like predictive thing is when you hit a target, you can kind of you can bug in both directions for quite a few steps and then see which one is closer. So we can see here, there's a rat here. It picked up a bunch of cheese and it wants to go back to the rat king. So what it's going to do is it's going to bug in both directions. So it bugged 1, 2, 3, 4 steps this way, then 4 steps this way. It's going to compare both of these to see which one's closer. It determines that this one is closer, and then it continues the path forward all the way to the rat king. And then from there, it can follow that path. And so because it worked, it didn't make the wrong choice and bug all the way around, which, would have taken way more steps, which is pretty cool. Some more thoughts. Just covering the image too, like I said, because we're predictive and we're simplifying every step, you can see we can generate pretty long paths. And I think eventually this will get optimized no, it's already actually optimized. We can see it goes all the way here, and this is, I think, within the radius to drop off cheese to the king. So it just generates nice long chains. Bug is pretty good, pretty efficient, handles a lot of tasks. You would definitely, there are cases where some sort of flood fill or BFS or whatever would find a better path, but for a general purpose algorithm, it works well. And what's also nice is those flood fill and more expensive algorithms or more optimized algorithms is they don't work well with exploring. Bug is great because if you don't know where you're going, bugging, again, you're just wall following and it'll help you explore the map. And then maybe later you could use a better flood fill algorithm. But if you're only going to write one, I think this is a great algorithm. The big downside, though, it is kind of complex. A thing I didn't talk about is the exit condition for wall following is I use the M line. Again, a bunch of the videos on BugNav talk about this, but to do the M line, I just check, is it within the bounding box? And then I solve y equals mx plus b to check if my position is on that M line. So like if I was here and I wanted to go talk to this one, I would start the M line here, and then I would iterate all the way around till I got to here because this is on the y equals mx plus b line. I know I'm on the other side of the structure, and then I can exit the wall following. Like I said, this algorithm is very good, I think, but it is kind of complex. And there's just a lot of edge conditions to think about that kind of make it annoying. For example, bugging does not like movable structures, which is frustrating. To get around this, I think one thing that is nice is once you have a path, it's nice. You don't have to worry about immovable structures. You only worry about movable structures when they're near you. So as long as you have a path and like, let's say there's like a robot here, what I'll do is I'll just move adjacent and then it'll be like, oh, okay, I can't move there, whatever. Then I'll move adjacent here. As long as I'm moving closer to the next one, I'm like, I don't really care. Maybe there's a robot there. And then eventually, hopefully, I can get back on the path. That doesn't always work, but for the most part, it does work pretty well that you already have the path. So as long as you can kind of stay near the path, you're probably okay. So that's one nice thing about generating long paths. Yeah. Next, let's see. What's cool also is you get to decide what is impassable. So to kind of avoid cats, what I ended up doing, back when cat vision was more important, eventually they kind of nerfed it. But it used to, because cats would just kind of follow a set path while they're doing their waypoints. But it used to be I would mark the cat vision as an impassable thing, even though obviously it's passable. But if the cat is looking in that region, I would just say like you have to go on the outside of the cat visibility range, which is an easy way to solve that. You have to do loop detection, which is kind of gross. Sometimes it'll just get stuck in these little loops. So you can kind of look ahead in your path and see like, hey, am I repeating a pattern or something like that? In which case you'll remove it. For narrow alleyways, someone, I forget who it was. I think X Square said Complex Merlin. I could have that wrong. Had the idea that you can pick up allies and then place them behind you if you're in narrow pathways, which is kind of fun to do. If you ever are doing micro and you get off of the path, because this algorithm is pretty flexible, you can just ask like, is there a path from where I currently am to the start of the path that I already calculated? In which case then, you just have to calculate these couple of squares instead of like redoing this entire structure. But I think redoing the entire structure really isn't too bad either. And then also you have to turn a lot for this year because of the vision cone. But like I said, I liked it a lot. I think I'll continue with this pathing bug thing. I would like to optimize it so it's a little bit faster, but my favorite pathing algorithm so far. The next section is micro. So the goal of micro is obviously at the combat is you want to calculate 4 different things. We want to calculate where we want to turn, where we want to move, what action we want to take, and the order of these things that we're going to do. And that is the goal of micro. And we want to do this in a bytecode efficient way. So I think the first thing to do is just like, first you want to decide what your strategy is going to be. And so you kind of write everything down. You have your damage, your cheese, your cooldown, and you decide roughly what you want to do and what are the things that you want to measure. And then from that, you're also going to look at what your environment is. There's a lot of stuff in the environment. There's nearby allies, nearby enemies, structures. There's the health of nearby rats. Are you moving towards the objective or away from the objective? Is there a cat nearby? Are there things on the map like cheese or dirt that you should play with? Are you protecting your ally king or are you attacking an enemy king? Are there previous traps on the ground? So we need to take all of this input and somehow calculate an output. So the traditional like X square micro, it uses, what its idea was that for each move state, you should calculate a bunch of like, I guess, metrics, like how many enemies, allies, what actions you can take, and then you write a comparator function that checks between those states. I think for this year, that specific strategy is a little bit too expensive. Like you just can't have, 600 states or whatever, and then write a comparator function between them. So I think instead, we kind of have to optimize that. And instead, what I ended up doing was kind of doing some bit packing with longs. And I'll talk more about the structure a little bit in the future. The idea is for each direction, for each move possibility, and there are 9 different moves you can make, so 1 of each direction, or you could stay center. Each one of these moves will be represented by a long, and then I split the long up into bytes depending on the direction I want them to look. And then I'm going to have a bunch of these structures. So there's going to be a move turn score. And this is just like, if I move here, how many allies can I see and how many enemies can I see and how many enemies can see me if I move here? That'll be your move turn score and a whole bunch of stuff. Then I'm going to have one of these, again, this whole table structure for all of the actions. So rat napping, bite scores, throw scores, and trap scores. So it ends up being like 600 states, but you divide it by 8 because I'm putting a lot of these into longs. It's a little bit more optimized and it's somewhat manageable. So why am I using longs instead of just doing an array of 600 ints? And that is because we can use the single instruction multiple data primitives. What's nice is, let's say, going back, so this move turn.add row towards objective OX11111, let's say going towards the objective is worth 16 points. And that's what we just decide. No matter, and let's say it's north. It doesn't matter which way I'm turned. As long as I'm headed towards the objective, you get 16 points, OX10. And if that's the case, we, instead of adding, 10, 10, or OX 10, 10, 10, 10, 10, 10 to all of these 8 times, we can just add a single int that'll increment all of these all at once. And if I move to a position that allows an enemy to see me, I actually need to subtract a couple of points, but it doesn't matter which way I'm turning, all of those should be incremented. And so by using these longs and separating them into 8 bits a piece for each of the 8 directions, I can do these operations, very quickly. I'm just doing the single instruction, multiple data, and I can add this entire row, which is very nice. You can also do some fun stuff with triples, since your vision cone is just the 3 squares in front of you. For those, you can automatically use, we're going to talk about Jinja later, but you can use Jinja to pre-compute those triples. And so instead of adding to forward, left, and forward right, you just add a single int that automatically adds the scores for each of those directions correctly, which is nice. So as part of this, since we're only using 8 bits per direction, each one that you can have an integer overflow of 256, and then it would spill over into the next direction column. So you need to be careful about that. There's also negative. I was using negative numbers. So like if an enemy can see me, or if an enemy can bite me or rat-nap me or something, like that's subtract from the score. I was using some subtraction, but the bitwise operators get a little bit annoying. Like if you're multiplying through the rows of negative numbers, I found it easier just to have a move score negative that I then eventually subtract later, which makes it easier, and I don't have to worry about integer underflows or overflows because I expand it to a full int. But anyways, so we're going to calculate, like I said, one of these big tables. So this is 9 longs, and then they get split into bytes for each direction, and we're going to have 6 of them. One is the positive move turn score, one is the negative move turn scores. Then if I can rat nap, and again, rat nap depends on your direction. If I can bite in a particular move direction, there's a good throw target, which is a little bit, kind of breaks the pattern a little bit, but we'll talk about that. And then if I can trap anywhere, and you have to move and look somewhere to trap. And then once I've calculated these 600 states, it's just a big unrolled if statement. I think it's like 6,000 bytecodes to check all of the 600 states. But it's just, I go through one by one. I think, I show it later. No, I don't. Yes, I do. Like I said, I just go through and say what is the base score. The move turn score is the move turn score minus the negative score. And then if I'm able to take an action, I see which action is best. And then if that particular move is better than anything else I've calculated, that's my new thing. So we do need to score things, and I think this is where the real strategy of micro comes in, is like determining the proper values for all of these things. Like one of these scores is, am I moving towards an important objective? I assign this 15 points, and this is just a number like I just use in comparison to other things and kind of tune. I wish there was a better way to determine these. I think ideally we would use machine learning and many games to kind of do a gradient descent and figure out the most optimal one. And maybe this is what people are doing. Like there's a lot of people that are testing in live queue, and maybe they're doing parameter tuning this way. I didn't get to that point, but it is interesting. But it would be nice if there was a way, that value calculator that I keep talking about, to determining what the proper value of these actions are. But anyways, I said move towards important objective. I give that a score of 15. If you're moving adjacent to it, I said 7 points. I don't know. Moving, then there's important objectives, and then there's just objectives. Like if you're just exploring, it's not that important. I would still like to go toward the explorer target, but I give it 4 points, 8 points. And then again, I multiply these out into rows. So it's not, it doesn't matter which way you're looking when you go to one of these things. So we just add it to all of the possible directions. And then there's other things like move away from the cat. Am I strafing? You get extra movement cooldown if you're not looking in the direction you move. I was doing standing still penalty. I ended up getting rid of it. The code doesn't actually do anything with this. I thought it would be good to kind of have units move around, but I don't think it actually makes a difference. Can I see an enemy? Which is nice. Are they on the border of my vision? I would prefer to be looking, have them in my vision cone as much as possible so they don't move out next turn. So I give more points if they're kind of in the middle. Am I standing on a trap? That's probably a safe place. And if I have low health, it's definitely much safer to be on a trap. Am I near an ally? So I got rid of this one. I just left it here to talk about. I think picking these things is kind of critical. So one thing that I noticed is I don't like it when my allies kind of jumble up or they stand too close to each other. Really you want them to surround and kind of leave the enemy's vision cone so it's easier to rat nap them. And I thought at first that this was maybe I should apply a penalty for being near an ally. And I realized I think this is wrong. I realized I was measuring the wrong objective. And I already kind of said what the correct objective was. The real objective wasn't that they were bundled up, which is not a bad thing. Like if an ally gets rat napped, like it's good to have another ally nearby so you can rat nap them back and steal back. But I realized really what I'm trying to measure is not that I'm not trying to negate because they're too close. Really, I don't want them to be in the enemy vision cone. And so I realized like, this is not the objective. This is not what I should be measuring. This is the wrong value thing. Instead is I should subtract if I'm within their vision. And so that's what I ended up doing. So more of a case study on picking like the correct metric to measure. These are the negative scores. So can an enemy bite me? Am I in the enemy cat vision? Can an enemy rat nap me depending on positioning or health? And am I in an enemy vision score cone? And then these are the different action scores. Again, I'm just kind of making up values and hoping for the best. And you just kind of tune them. But can I bite a king, a cat, a baby? Can I rat nap? If I rat nap and rescue someone, I mean, that's huge. Should always do that. Can I throw, depending on who the throw target is? And can I place a trap? Trapping is confusing, and we'll talk a little bit about that one later. So how do you calculate all these things in an efficient way? And we're going to talk more about this again, talking about code is all over the place, but we're using code gen switch statements. And so this is update in enemy vision score. So again, we're going to talk about Jinja later, but you can use Jinja to generate Python code. So what we're going to do is this function takes in an enemy location and an enemy direction, and it's going to calculate the relative offset from my location to the enemy location. And this gives us, translational invariance. So momentum is conserved, which is a joke. And so we have a switch statement that contains the relative offset. And so for what we're going to calculate, for all of the possible moves I could move, will I be in the enemy vision cone? This is a Jinja function it's a Python function I wrote and gave to Jinja. So we can calculate this, because it's all relative positions, we can calculate this in Python before it gets calculated in Java, making this super efficient. And so what's going to happen is only in certain enemy position offsets will I be in vision depending on my move. And what happens is if those conditions are correct, so if there's an enemy at -4, -3, and they are looking north, so they're kind of in the bottom left corner looking straight up. It is only if I move left. So if I move left -1, -1, or I guess up by 1, that I will be in the enemy vision. And so it is only for those moves and that enemy offset that I will then need to add this negative score, and which is pretty cool. And we're using these switch statements because as we'll talk about in the bytecode hacking section, jumping to an offset within a switch statement costs 1 bytecode, which is amazing. These switch statements end up being the bytecode instruction is just 1, and it's just a giant map, and just the way Battlecode works, it is just 1 bytecode. So very bytecode efficient. And so to calculate this whole thing, if an enemy was at this offset, -4, 3 looking north, it will cost, 1, 2, 3, 4, 5, 6, 7, 8, 9 bytecode. That's it. So we can do this very fast. And then obviously there's the packing arguments and calculating the offset. So we're talking like 50 bytecode for this, which is very trivial. Compared if we were to do this in Java, this would be extremely expensive. Calculating through, doing the vision cones like this, I shouldn't say extremely, but we'd have to iterate through all the positions I could move. And for each of the enemies, we're talking like hundreds and hundreds of bytecode. So using this code gen stuff, again, we'll go a little bit more in depth on this stuff, but we can save a lot of bytecode and make the micro code much faster. And the real benefit is this in-vision code that we can write within Python Jinja and then call, and then just only have these add statements, and that's it. Trapping is difficult. I don't have a good solution to trapping. Again, I just kind of use some heuristics. I think, again, we need a better value calculator sort of thing to like equate the value of things. But I just kind of said, do I have enough global cheese to support trapping? Is the current rat cast less than 2 times the trap cost? Like if it's cheaper just to build rats, then let's just do that instead of trapping. And I also just use that as a proxy for guessing how many rats the enemy has. If they're spawning rats for 30 and I'm spending 40 to trap them, I'm obviously losing money. Another variable that goes in, is this rat important? Does it have information? Does it have a lot of cheese? In which case you probably should trap. I also make sure that there's no nearby traps. Like it's frustrating. Like you could have like a 10 health enemy rat come in and trip like 3 traps all at once. And so we spent 60 cheese to kill a rat that only had 10 health. So I want to make sure that all my traps are split apart. And then am I also defending an important objective? In which case then I'm more likely or more willing to spend more cheese. But anyways, those are some of the variables I used for calculating that. And this we already saw, but this is just, you need to sort through all 600 of those states to determine which state is best. And yeah, like I said, I just use CodeGen. We'll talk more about that later to just pump out all of those 600 conditionals into if statements. I think a very important part of this too is just having a function that dumps out the state. And so sometimes rats will make very interesting decisions and you need to debug it. I wish there was a way to disable bytecode counting in local mode, but there isn't. So what I ended up doing was saying like, I would watch the replays, local replays, and then I would see if a rat does something interesting. I would get the rat ID and the round number, and then I would dump the state for that particular one. Because I think this dump state code ends up taking like 1,000 bytecode or something. So you just can't run it every turn. So up next is bytecode optimization, my favorite section. I like this bytecode stuff. So we're going to talk about why bytecode was used as the metric. We're going to talk about how the instrumentation works. We're going to talk about what bytecode is, what it looks like, and then we're going to talk about the bytecode structures. There's a bunch of guides on how to optimize bytecode, and it talks about like using local variables, not instantiating classes, unrolling for loops in a particular way, and those do save you a couple of bytecodes here and there, but they don't really influence the design of your program. I think these structures that I'm going to cover, the string builders, single instruction multiple data longs, and code gen switch statements, which we've technically already covered all three, but a little bit more in depth, these are the things that like really influence the design of your program and are the things that really save you bytecode or not. And these are like the tools that you need to pluck out of your toolbox when you're trying to solve, a challenge on a future competition. If there are more, I think these are the main three. If there are more, please let me know. I love thinking about this stuff, but these are the three I could think of. So first off, why bytecode? Why was bytecode used as the metric for, evaluating turn length? First off is why should Battlecode limit turns? Like, why not just let people run whatever code they want? And I think the answer is more fun. And I think it's also, it would just not be possible. You could imagine like if execution time was uncapped, you'd be incentivized to run extremely expensive algorithms pretty sloppily. For example, you might run a full map BFS on your turn, and then maybe you turn your robot, you have a little bit of more information, you're almost incentivized, and if you want to beat other people, you're going to have to the competition it's not about building the best bot, it's about building a bot that beats other people. If they're doing a BFS after turning and you're not, they have just a slight edge, and so everyone is just going to be incentivized to write more and more expensive bots, which just isn't fun. And, we just need a way to keep things fair and fun. And so part of the fun is you can't do everything. So you need to decide what it is that you want to do. And that restriction is what makes it fun. Otherwise, otherwise everyone's just going to be running the same algorithms and, just doing things optimally. Although what is optimal is, we keep talking about this value calculator, is not really well known, but I think it just makes it more fun. And that's why we should restrict things. And otherwise, like I said, everyone's just going to be running the same default algorithms, which just is not fun. So why not base it off of time? That seems like the obvious choice. Like every turn you get 10 milliseconds of execution time to run all of your code. And if this was possible, I agree this would be the best solution, but it's not possible because it is non-deterministic. 10 milliseconds of time on my machine is not equal to 10 milliseconds of time on someone else's machine, and specifically the game server machines. And so maybe your bot times out and you don't know why. It would be a very frustrating experience to debug and just not fun. Java's also garbage collected. So maybe you get a garbage collection spike or something. I mean, maybe you could probably work around that, but still, it's just too tricky. So instead, bytecode was decided on. So when you compile Java, it gets compiled down to bytecode, which is like a portable representation, and then that can get compiled down to native on further machines. But this bytecode, it's extremely portable. It is the same on everyone's machine, and so we can explicitly just count that. And it is just very deterministic and very easy to reason about, even if it doesn't really map to reality, which is kind of some of the things we're going to exploit. Like I said, bytecode, if you don't know what it is, it's just the instructions executed by the JVM. So when you compile Java, it gets compiled to .class files. Those .class files have all the bytecode for that particular class, and then it is translated just in time. There's a couple different optimizers too, but it gets computed or translated into machine code on the host machine. The JVM language is very portable. It's like the stack-based virtual machine. It's pretty fun. It's not that complex. Actually, we can just open it up. Here's a list of instructions. What was I saying? Oh yeah, so the instructions, there's really not too many, and if you go through them, they're really not that bad. Look at these, I want to store a float value into some local variable, I want to multiply to some floats, I want to get some static or a field, I want to do some adding, push the value 0 onto a stack. All of them are very simple instructions, and they just make up a little virtual machine. If you've never played with virtual machines before, I don't know if the JVM is the right virtual machine to make, but it is fun to like build your own virtual machine. I'd probably go register-based instead of stack-based, but they're both fun. Register-based would be like the instruction set architectures that if you do any assembly programming, you're more likely to be introduced to, like x86, x64, or ARM, which is either your Intel computers or like the new Mac chips or your phones. But yeah, it's fun. So we have this little JVM. This is what the bytecode actually looks like. So we have this little function. It's called sample function. It's going to print out this string. It's going to create some accumulator variable. And then for I equals 10 all the way down to 0, add the accumulator. So we're just, adding 10 plus 9 or 9 plus 8 plus 7 plus 6, blah, blah, blah. And this is what it looks like. You can see we're going to get this static, which is this field from the constant pool, Java ling syst out. Then we're going to load a constant, which is load constant, number 70, again from the constant pool, which is the string. This is a sample function. We're going to invoke virtual, which just means we're going to call a function. We're going to push the constant 0 onto the stack. So that's what the 0 is for. This 0 says we're going to store the top of the stack into local variable 0. We're going to push an integer. We're going to store into local variable 1, so the second one. This is I. We're going to store, so I is equal to 10. We're going to increment variable 1, which is I by minus 1. We're going to load variable 1. We're going to check if it's less than. If it's less than, we jump to line 27. We load 0, blah, blah, blah. We can see we're loading two local variables here. And then we're going to add them together. Then we're going to store it back into a local variable, which is n. So we can see it's pretty simple. Like if you don't know what one of these is, you can just go and check up what it says on Wiki, and it's really not too bad. So how does MIT Battlecode actually instrument our code? And this is pretty fun. And whoever wrote this, very clever, interesting code, I should say. I think clever code. It's a pretty fun implementation. So what it does is it uses this framework, the ASM.OW2 framework, which is an all-purpose Java bytecode manipulation and analysis framework. And so it's going to take those .class files that you submitted and also the class files for like the Java utils. And what it's going to do is it's going to instrument each basic block. So a basic block is just a region of code that is always executed together. There's no jumps in or outs. And you use this a lot in like decompilation. Like I play CTFs, capture the flags. And so you'll decompile some like binary or something. And a basic block is just like, a block of code that usually assembly instructions, but in this case, JVM bytecode, that is always executed together. And so what it'll do is it'll count the number of instructions in one of those basic blocks. And then at the very end of a basic block, there's this function, end of basic block. What it'll do is it's going to insert load constant, the current bytecode counter, so the number of bytecodes in that, and then it is going to call this function increment bytecodes, which is a member or method as part of robot monitor. So it's just going to put a variable on the stack and then call a function. And so every time your code enters this basic block, it's going to execute all of those and then increment the bytecode counter with the number of instructions in that basic block. So it's pretty cool. So it is like not dynamically, it is modifying the bytecode that you give it and instrumenting it with all of these little calls. So if you had a lot of basic blocks, you're going to have a lot of calls to robot monitor, but obviously the robot monitor calls aren't added to your bytecode. It's this static bytecode counter variable that is actually incremented. What actually gets instrumented and what isn't instrumented is some pretty interesting code. It's a little bit messy, but there's things like if you're going to allocate an array, each allocation cost one, so there's special casing for that. Regexes, which we're going to talk about in the future, are also specifically instrumented because there was some cheese with that. And then there's also this method cost file, which specifically bypasses the basic block calls. So the Battlecode engine specifically whitelists these functions. So if you call clock.yield, it costs 0 bytecode. And if you call, map location isn't adjacent to, it costs 2 bytecode. And so these are most of the functions that are outlined in the Java docs, but this specifically says how much each thing cost. So we can see if we want to write to that shared array, it costs 50. One very interesting thing that they do, and we're going to be talking about, is they specifically whitelist a whole bunch of string functions. I'm not sure of the historical reason for this, but this is something we will be abusing very shortly, and I've already hinted at, and you probably already know, is the string builder and string buffer stuff. For some reason, all of these cost 1, and we can do some fun stuff. I'm going to talk about it in the future. Some people say that it is absolutely busted. I don't think it's absolutely busted. I think it's just you can do fun stuff with it. That's all. Yeah, anyways, let's talk about it. So cool. So the string functions all cost 1 bytecode, which is fun. And I think I could be wrong. Someone needs to double check this, but I think the string functions that are not listed on that actually cost 0 bytecode. I think the way it's implemented, but someone should verify that. But someone in the Discord said that they were thankful that some at least some of the string functions cost a lot. I did some quick testing. I don't think that's the case. I think if they're not listed, they're 0, but I could be wrong. Anyways, most of the string functions are listed, and the string functions that we use are the ones that are listed. So what can we do with the string builder? So we have some code on the right. We're going to say string builder append this location, and we're going to serialize. So location.x bitwise shift left by 6, and then or with location.y. So we can serialize a map location and put it in the string builder. And so we're going to append 1 location, 2 locations, 3 locations, and then we're going to grab those locations. So we'd have to deserialize it, but location 0, location 1, location 2. And then we ask how many bytecodes that was. And then I'm going to do the same thing with an array list. I'm going to make a new array list. I'm going to add a location and then get those locations and then return it. And we can see that the string builder only costs 34 bytecodes and the array list costs 129 bytecodes. So if you're using just a general container for map locations, which is usually what you use the structure for, you can see that the string builder is way more efficient. The array list is just not good at all, unfortunately. I kind of wish that they whitelisted the functions for array list and made them more reasonable, but just to like kind of promote good practices, but it's not a big deal. It is like 4 times cheaper. So it is a great container to do for that. But I think, again, I'm going to assert that I don't think string builder is like busted. I think it is good, but it is not busted. And for example, we can see, one thing I didn't do with this is I didn't deserialize it. So again, I should be deserializing it right now. This is just an integer. I need to deserialize it into an X and a Y and create a new map location. So this should be a little bit higher. Instead, like if I'm using a fixed size list, and we're going to talk about the different like containers that a string builder is trying to implement, but one of them is, a fixed size array. Like I have 5 rat kings, so I need to store an array of 5. If I store it to 0, 1, 2, 3, and then I read 0, 1, 2, and I also have to assign because it won't let me just insert an arbitrary expression on a line. I have to assign it to something. So this is taking an extra like 6 or 9 byte code. It only costs 30 byte code to do this. So it is cheaper than using the string builder if you have a fixed size array. You don't always have a fixed size array, but if you did, a string builder isn't like some cheat code. It's just like an array list that allows you to do interesting things. Some people, if we go back to some people might point out that the index of allows you to search through the container. It'll scan each element until it finds the element that is equal to something. So we can check, like if you had a long string array of a whole bunch of walls, you can see if that walls set contains this object. And that does sound busted, but it's not actually busted because we have containers that have O of 1 lookups, which are hash maps. And because we're also dealing with a fixed size map, it is not actually that busted. Instead, you can use long maps, which is a structure we'll talk about later, to get O of 1 lookups. So any operation that we want to do, we can construct a data structure that gives us the O of 1 lookup, either between an array, a linked list, or a set. The reason string builder is busted is it gives us O of 1 for all of the operations at the same time. But again, I would argue I don't know of any abuse that specifically uses the fact that you want an O1 of this lookup pattern and an O of 1 of this lookup pattern at the same time. I think for when I go through my code, I could have used an array, a linked list, or a set for all of these things. I'd have to implement all 3 of these data structures, but I think I could have made a fast version of all of these without using string builder that would have just been as fast. But string builder is nice because it just gives you a super fast, easy container that you don't have to think about, and no matter what your use case is, it is always O of 1. But like I said, when you look at like the code gen solutions for like convolution operators and stuff like that, like they're using longs. They're not using strings. And I think at the end, if you can do things with longs, it is probably faster than a string builder. But anyways, like I said, so string builder, it's like the super container of map locations, and you can treat it, you get the best of array, the best of a linked list, and the best of a set. And specifically, like if you're doing index of, like this is very easy on a hash map. It's just O of 1, and we could be using a hash map for the whole, this is 60 times 60, so a character, or you can also do it with a bit set with longs for each location. You could do it, but instead you get it for free with a string builder. It just costs O of 1. If you want to iterate through each element, obviously you can do that very simply with with an array. With a linked list, you're going to have to step forward that many elements, so it's not necessarily n, but it is something depending on how many elements forward you're looking, and that doesn't really make sense to do in a set. I guess this would be like O of 360 of the map dimensions to figure out if you want to iterate through. If you want to know the total number of elements in the set and iterate through each element of that set. If you want to create a new one, Creating a new string builder costs nothing, O of 1. Creating a new linked list, I guess it's O of 1. Creating a new set, I don't know, it costs 360 because of that bytecode array operator overhandling, so 360 bytecode, I guess. If you want to append, this is tricky because normally for an array, you're going to have to create a new, like if it's not a fixed size, you need to create a new application and copy all those elements over. Array copy, I think, is also whitelisted. It might just be n, which is somewhat fast. But for a linked list, like this is O of 1, and this is useful for like pathing. Like we had that path array for the predictive bug. We needed to add elements to the end repeatedly. So obviously we could use a linked list for pathing. We don't need any of these operations. We could just use a linked list. And so it would be fine. It's just nice that string builder does it for us. And then a set, it's kind of weird to append. Again, I already said all this stuff, but string builders it's just a very great utility library that you use as your array list because we're not allowed to use Java utils array list. It just becomes your array list. If anyone has any abuse that you used because you're specifically using it where you're taking advantage of two of these different structures at the same time, I would be curious, but I couldn't think of any case where that was actually true. But there's a bunch of these implementations all over the place. They're just called fast implementations. You can find them in Discord open source on GitHub. Some people implement them differently. Some people do like a little caret operator, and then they actually do like the string values of the application. Other people, like myself, I find it easier just to encode it into like each character within a string builder is 16 bits, so you can encode a bunch of information. The big downside of using these string builders is actually the function calls themselves. Like normally you wrap one of these fast arrays into some class and you instantiate objects of those, and it costs a bit of bytecode to do that. But if you use CodeGen templates, you can inline them, so you don't have to deal with those function calls, which is what I ended up doing. We're going to talk more about Jinja 2 in the future, but I ended up creating a macro library for fast arrays. So you can say like whenever I want to create a fast array for walls, instead of like creating an object, it's going to call this macro code, which is going to do public static string builder walls fast array equals new string builder, and that'll put that right here. And then when I want to like add an encoded element into the wall structure, instead of calling the fast array library, it is just going to dynamically insert a string builder statement right here. So I avoid that that function call and potentially multiple function calls for doing the encoding and decoding, and I can have like nice clean code like encode location. This won't be a function call. It'll just like continuously inline itself and just be much more efficient. So I save probably, you use some of this stuff like in very deep into a for loop where like bytecode is critical. And so, you can save like, 5 or 10 per loop, which adds up very quickly. So using fast arrays with Jinja 2 can definitely save you quite a bit of bytecode. The next interesting bytecode structure is one we've already talked about, but is these like single instruction, multiple data longs. And it is because it allows you to do multiple operations at the same time. And I mean, this is also, I think, where like a lot of the speedups of like GPUs can come from too. You can do many of these operations at the same time. I think modern CPUs also have like 128 and 256-bit registers that you can do these things for. I think some of that's for like cryptographic and like AES primitives and stuff like that. But being able to do multiple things at once, very nice. And so if you wanted to compare, you can think of comparing two longs as doing 64 if statements at once. If you could somehow encode a problem into that, which is the hard part, but if you could, if there was some way that you wanted to compare, you're essentially doing 64 if statements all at once because it is doing a bitwise comparison bit by bit. If you're doing math and bitwise operators, you can potentially do either 2, 4, 8, 16, or 32 or 64 operations all as once, as long as you can encode the problem that way. But like what we were doing for the map direction set, because I was splitting the directions, 8 directions into a long, I was doing 8 operations per time when I wanted to add a score. So like if I wanted to add that score 16, I'm doing 8 operations all at once, which is very nice. There are some people that do like bitwise convolutions, and I think they were like multiplying stuff together. And so again, that was another use case of this. And this kind of reminds me of I was working at an AI company, and they were talking about, I think some of the machine learning people are using 4-bit floating point numbers, which is crazy, but it allows you, if you have 4-bit floating point numbers, you can really pack things densely and really abuse these like floating point single instruction, multiple data things. So the two uses I can think of for single instruction multiple data longs is the map location sets, which I already talked about. Again, we can store like walls and other structures into one of these long bit sets, and then you can use that as a container to ask queries like, is there a wall or a scene here? But then you can use it as a mask for like merging things, a mask for pathing. You can merge multiple layers together with a bitwise OR. You can do some convolution. I think it was useful in the SRP tiling year, which was last year, to see like if a pattern will match. So very interesting structure to play with. And then again, this year was the move turn score, where you split the long into 8 for each direction, and so you can add an entire row at a time. Very fun thing. Another one is structure that breaks things, not breaks things, but is good to abuse, is the code gen switches. So switch statements take a single bytecode. So we have this switch statement here, switch, and then case 1, 2, 3, 4, and then break. If we see what that looks like when it gets converted to bytecode, it gets converted to a single table switch statement. And so this whole thing, even though it takes up 32 bytes, it is only 1 bytecode, which is awesome for abusing things. So we can see if the case is 1, we're going to jump to offset 32. If it's 2, it's going to jump to 43, blah, blah, blah. But basically, this kind of gives us like a hash map for instructions. Like you can jump to a particular state where you want to do things. And so we abuse this with CodeGen, this is the example we already saw, but we abuse this with CodeGen to pre-compute things and then jump to a known state to really save a lot of bytecode. I won't cover this one again, but we saw that we were able to encode a relative state here, the switch state, enemy position .x, .y, and what direction they are. Then we use Python to compute a bunch of stuff about that relative state, and in the end we end up with just this. I realized actually you probably can't see this in the video. Let me move this, but this is what it ends up calculating. Move turn score negative, and it's just these plus or minus. So if you're in -4, -3 looking north, if I move to the left, then I'm in the vision cone. And this is probably only like 9 bytecode or something like that. And the jumping to this case instead, if we didn't have case statements, we would have to do, if you're in this state, do this. If you're in that state, do this. If you're in that state, do this, which would take, a lot of bytecode. One frustrating thing when doing these code gen switches is you will probably run into this pretty quickly. Error code too large. Technically, a Java function or method can only be 64 kilobytes long, which is annoying. And it's actually technically less than that because the Battlecode instrumentation is going to inject more bytecode, at the end of each basic block, which if you have a switch statement, it's going to be at the end of every single switch statement. And so it'll be even less than that, which is annoying. So I think there's like 2 solutions to this problem. One is you have too many states, so you're trying to encode too much information into your switch statement. And so what you can do is you can code gen individual functions. So you'll have a switch statement that then calls functions, which are code gen functions. And so you can kind of, strip away some of that state. And the other thing you can do is maybe the logic for handling each state is too complex. And so instead, what you'll do once you're in a particular state, you'll then have it call a function with arguments, and it'll actually do the thing that it needs to do, which are 2 solutions I found for kind of getting around this error code too large. But like I said, doing this pattern, you can save a lot of bytecode because you're calculating everything beforehand, which is super nice. It is tricky thinking about it is hard to reason about this code, like what you can compute in Python and what you can compute in Java and like when that computation is happening. But once you get it working, it's pretty nice. Another 2 other use cases is you can do arbitrary loop unrolling. So let's say you want to unroll a loop, but you don't know how long that loop is going to be. So let's say this is a silly power operator. I don't know how big the pow operator will be. Normally you just do math.pow, we're just using it as a silly example. But if it was n, because case statements fall through, if it was length 6, then I'll do it. And then if it was length 5 or 6, it'll fall through. And then if it's length 6, 5, or 4, it'll fall through. And so basically I'm able to arbitrarily unroll loops of arbitrary length, which is fun. So another fun use case. So instead of, it would cost, 7 plus 7 plus 7 plus 7 plus 7 plus 7 to do this, but instead I get it for free. Another fun thing that I couldn't find a use case for, but was included in Java 21, is that they now have switch expressions. And I think it could be useful. So, which means that you can use a switch statement as an R value for like an assignment. So normally you would use a switch to like perform an action, but here we're using it as the R value and assigning it to this location. So I think you might be able to use it for like an efficient serialization, specifically for like code gen. It seems interesting. I don't know what to do with this yet, but I think if you had like a complex int-to-int mapping or something like that, you could potentially squeeze out some bytecode using structures like this, but something to think about. So those were the 3 things. I think there's probably more like actual abuse and stuff out there that people just haven't found. But again, very fun stuff. I found this, or someone in Discord was talking about this a couple of years ago, but someone called Greg Little, my name is Stuart, so if we combined, we'd be Stuart Little, which would be fun. But they found a cheese abusing string regex, and they were able to create a pathing algorithm using that. I highly recommend checking out the blog, and they also link their code there. But you can see they do string matches on this regex, and depending on certain conditions, they can kind of expand this map and find a very efficient pathing algorithm. And the way that the real cheese, like I guess the insight that regex gives you, is arbitrary width modifiers. And so these A's and B's and C's will be the width of the map. And so because you can say like, if an element is above my current element and ask that in a single query, you can, it gets a lot. It allows you, it gets pretty far. And also, obviously, regex, you can do a lot of stuff with regex and replacing and stuff like that. So just super efficient, but pretty fun. After this was discovered, they obviously patched regexes, so you're not allowed to abuse regexes anymore. But I'm sure there's more fun stuff out there. And I was thinking, like, what if you were to find a new abuse, what would it look like? And I think it would need to speed up something we already currently do. And the expensive things we do are pathing and micro. So pathing, a little bit tricky, like some of the fun stuff people do with like those bitwise convolution operators to do the fast flood fill maps. I think people are, it's pretty good. Maybe there's something there with string builders. Like I keep looking through the string functions, hoping to find, some way we can speed up pathing, but I haven't figured it out. If anyone figures it out, don't tell me, like abuse it first and then tell me at the end of the season, unless it's too abusive. The other way would be like in micro, like an annoying thing we had to do this year was that 600 integer compare. Like, could you encode that problem into a string and find like the largest int in a string? I can't think of a way. Like maybe you could like sort and do a binary search, but you can't sort. If there was some way you could abuse string builder to find the largest int out of 600, that would, save us 6,000 bytecode, which would be amazing. But I couldn't figure it out anyway. And then there's also like, if you could figure out a way to use string builder or something to modify multiple elements in a string element by element wise, like you need like some sort of zip operator or something like that. If you were able to find that primitive, I'm sure you could do a lot of fun stuff. But again, I wasn't seeing a way to do that with strings. But anyways, fun stuff. The second to last section is Jinja templating. So this changed the game for me. I think I saw this in a write-up by Team Omnom last year where they talked about using Jinja templating. So I think a lot of people use Python to code gen, but it's just like a Python script that then pumps out a Java file. But using Jinja just made so much sense. As soon as I saw the write-up and they mentioned Jinja, I was like, duh, that just makes sense. It's such a cool idea. And so a couple things I want to talk about. One very useful thing you can do with this is debug statements. And so there's a couple of things that make this very interesting. This is what my log looks like. We can see when I log a statement using this debug extension, which I'll show what it looks like in a second, it'll print out the file name, the line number, the total bytecode, the bytecode since the last call, and then it'll print out all the variables and it'll use this like equal syntax. Absolutely amazing. Again, this is stolen from the last team and then expanded upon. And so just this debug call expands to all of this information automatically. And it's also great because I hate doing this equal sign. Like before this, I would just have like locations on a log line and I wouldn't know where they would belong. Like sometimes you try to put like a unique string here and then you'd have to like find the string in your code. Right now, like whenever there's something interesting, I can just copy this. Visual Studio Code will just like, pop to that file and that line number. I can see what the variables are. Like this is an expression too. This will get evaluated in real time as this gets converted from Python to Java and then the Java is executed. Just so much. And what's also great is you can disable it on release modes. So within the debug extension, I specifically say what files I want debugs lines to be turned on for. So it used to be previously like if I didn't want something, I would go and comment a bunch of lines out and it was just really messy. Now I can say like, hey, if I'm not doing anything with trap micro, like just turn it off. I don't care. And maybe because I'm just doing something with bug. Super nice. I can also turn all of them on and off. And I can also turn the bytecode on and off. Just makes things so simple. And this is what it kind of looks like at the end, like show the bytecode, show the difference, show the current bytecode number, and then show the message and then the file name and the file no. Again, the base of this was stolen from this file and then expanded upon. So debugging, super great. And like I said, when I build a release build, I disable all of debugging because doing the string formatting probably takes like 500 to 1,000 bytecode, and I don't want to comment everything at the very end. It does it for me, which is nice. Loop unrolling, we've already covered this a whole bunch of times, but each loop iteration costs like 7 bytecode, so you can save just a whole bunch by just unrolling all those loops. And because we're doing it in Jinja, it just you can have the Java code in between. And so you're just basically writing Java, and then when you need Jinja, you just switch over to Jinja syntax and it just starts working. The big downside is that you lose IntelliSense, which is huge, but there's a trade-off. Next is release mode. Another common problem I had that Jinja fixes is I would want to test things locally, and then sometimes I would forget to remove them before I submitted before a tournament or something like that. For example, like if you go over the number of bytecode for a turn, I like throwing an exception so I can figure out why I'm over bytecode and fix it. But there's been plenty of times where I have forgotten to turn that off before I do a submission. And so now I have this release mode. Whenever I build something with release mode, so I do Python 3 scripts Jinja pi a -- release. It will check if I'm in release mode or not, whether or not to include the statement. So now whenever I want to submit something, I know that all of my local testing will not go into the submission build. And so we can see here, if not in release mode, the king was only going to spawn 4 rats. So if I'm doing some like local testing or something like that, and then I don't want a bunch of rats flooding the board, this will only spawn 4, which is super nice. And I can be assured too that I will not accidentally forget about this. And you can also do like A/B testing with this too. Just great quality of life feature. Next, we've already talked about, but these are the macros. So you can build entire libraries. You don't want to call functions because each function has a cost associated with it. But you can build these. You still want to write good code. Like I still want functions. Because I want to twig with things. And so what you can do is write these macro libraries that are all the functions are then inlined into each other. And then you just get nice, clean, efficient code at the end, but you don't have to see that. You only have to deal with the the macro library, which is much easier to write code in my opinion. So we can see this is my fast array macro library. So I can create walls. I can ask if it's encoded instead of doing the bitwise flipping and the contains and all that stuff on a string builder. I can clear and extend things. I can check if it contains and encoded, like much cleaner code than having to do like all the nasty string builder stuff. And then and it's also extremely fast because I'm not actually calling these functions. These get encoded into Java statements, which are then executed quickly. And then I think the last one is Jinja functions. So you can create functions in Python. So like this can ratmap function and expose that to Jinja. And then within your Jinja code, you can call that. This is very useful for those code gen switch statements. So I write these functions and then, I can then do the code gen, make the switch statements. And I just have, really useful utilities just to speed everything up. And it's all written in Python and you have your syntax highlighting and all that stuff. So another very useful feature of Jinja, which is why I think, most people should check it out if they haven't. Again, the big downside is you lose IntelliSense. You get some syntax highlighting, but no IntelliSense definitely makes things a little bit tougher. And I think also if you use like Copilot or something, like the tab complete doesn't work as well for AI, because I think the AI also uses IntelliSense. So last section, thankfully, you can probably tell I'm losing my voice. So thoughts on winning. First thing, I was reflecting on the importance of winning competitions like this when you're younger. And winning isn't everything, but it is just so important. And I was thinking about like, as you progress through your career, you're kind of like on this ladder and, you're just kind of ratcheting yourself up on this ladder. And saying that you won an MIT Battlecode, in high school or, in undergrad, that can be like, that doesn't instantly mean that you're going to be successful, but it just makes future success so much easier. Like it's just like a little bullet point that you can just put all over the place. Just so useful. And one thing that kind of frustrates me that I didn't really realize until this year that I was like, top 4 for one of the sprints. And I'm not saying this as a negative thing, I just didn't really realize was just how much of a coin flip it can be to actually win. It was like the person that was top of the ladder, X Square for sprint 2, I think they got kicked out in top 8. But even though I think most would argue they had the best bot, I think. I mean, maybe you could argue that. But even if it wasn't, I think it was like a 50-50. And I just didn't realize how much like being a winner for some maps, it just comes down to a coin flip. And when you're like, in high school or something, and putting this on your resume could be the difference between going to MIT and not going to MIT. just huge. I wish it wasn't such a coin flip. I think for future, I'm sure the devs already know this feedback, but like the cat it was not deterministic enough. And it's not just the cat. I think also the maps, like it just could just be that, your explore versus exploit strategy just like works well on some maps and works better on other maps or not as well on other maps. And during the final tournament, you just happen to get the maps that it worked well for. I don't like that it's so coin flippy, but I don't really know what to do about that. But anyways, thoughts on how to do better. So 3 years ago, I was on 40th. This year, I was in top 10, and I got top 4 in Sprint 2. So I got a little bit better. Obviously, I'm not a winner or anything, but I think thinking about what things that actually made a difference, and I think just experience within the Battlecode ecosystem is probably the most important thing. So I've been programming for about 20 years now. I'm 34. I have not become a better programmer in the last 3 or 4 years. I can pretty confidently say that. I have not learned any new Java or anything like that. My Java knowledge is the exact same as it was 3 or 4 years ago. Maybe I know a little bit more about bytecode. I think the only thing I learned about was Battlecode primitives. It's just like Battlecode specific stuff. And so I think if you're going to invest somewhere and you want to win, if your only goal is to win, then investing in Battlecode specific stuff is probably the most important thing. I was thinking you could learn data structures and algorithms, and that could be useful, but I think just learning general data structures and algorithms is probably not going to be as useful as learning the specific data structures and algorithms related to Battlecode. Because Battlecode just has a very specific way of doing things. I think also knowing a big one is the sprint maps, the sprint tournament maps, and I'm sure the tournament maps for all the tournaments. The devs like to do certain things, and I didn't realize there are a pattern to how they do things, like making inaccessible resources or narrow pathways or putting kings right next to each other. If you've never seen a sprint before, you don't know to prepare for that. But I think if you played a couple of years, you know what type of maps they're going to present to you in the sprints, and that's just a huge thing to be able to prepare for. I think also that's nice is if you build a framework. I realized that the first couple of years, I rebuilt BugNav every year. And I think it's a good learning experience, but that takes a couple of days. BugNav itself is very easy, but there's just weird edge cases and stuff like that, and making it fast and working the rest of your framework. But I think, once you have I really like my current setup, and I know if I do play future years, I'm set up. I feel within week 1, I can probably copy, and this is what the top teams, I think X Square mentioned that they just copied their previous code. I feel I could hit the ground running so much faster next year now that I have systems and patterns that I really like, which is just kind of an unfair advantage to someone coming in brand new. So I do think it takes a couple of years to really get into a system you like to be able to compete. So I think you could, on off season, if you were interested in winning next year, is implement all the pathing algorithms and the micro frameworks and kind of get everything ready before competing, because just hitting the ground running right when you start and having a good pathing algorithm, having your micro setup, having a good all your components routed together correctly in the state machines and all that stuff, and your debugging library, your Jinja templates, that stuff takes a week or so or 2 to set up, and having that already done would be just a huge leg up. I think another thing that really contributes to winning is definitely grit. I think my first year or 2, I thought that I was missing some strategy that would have enabled me to win. I was just missing some simple trick. I don't think that's the case anymore, especially after reading the write-ups from other people. I don't think it's anyone does anything super crazy or super unique. I think it's just a lot of grit. It's just hundreds of these little improvements that make things better. And I think, it's a huge time investment to be able to play. I hope for most people the time investment is worth it. I love it. It's a lot of fun, but I think it is a huge time investment, and you just kind of get in what you put out. You're just watching those replays, figuring out what's wrong, and just doing that over and over and over. And then the last thing that I think contributes to winning, I do competitive stuff in a different field called Capture the Flags. So I have a lot more experience in that than this, but I think also prioritizing your health too can be a huge advantage. I think when you're sleepy, I think back to my college days, I used to just not value sleep at all. And I think you just get sloppy, you write bugs, and it just slows everything down. So I think if some way incorporating before the tournament starts, how you're gonna, or just having a plan of how you're gonna manage your health, is something I wish I had done more of when I was younger. Thinking about am I still gonna get some fitness in? Am I going to get my 8 hours of sleep every night? Am I gonna eat just a little bit of healthy food? Can I manage life stress in a way so that I can fully focus on the competition? I think things like that can also have a big difference on your chance of winning. But anyways, that's it. Glad this is over. I am my voice is very scratchy right now. But I just want to say thanks to the devs and MIT for hosting. I hope you continue giving access to the public. Like I said, I'm an old person. I just love playing. It's one of my favorite times of the year, just competing and the vibes and the energy. Thank you to all the other competitors. Everyone's very respectful and kind, and I enjoy talking to everyone. And again, if anyone thinks I'm thinking about something wrong, I would really appreciate your feedback. Anything that I might not be thinking about the correct way would be super insightful. So anyways, thanks, and hopefully if everything goes well, I'll see everyone next year. Cheers.